Hello everyone. In this video, we're going to talk about how to solve first-order linear differential equations. When we talk about first-order linear differential equation, it's going to be in the form of y prime. So we've got a first derivative. That's where that first order is coming from. Plus p of x times y is equal to q of x. This p of x and this q of x are functions, and they're going to be functions that are continuous in terms of x only. So if I have something that can be written this way, then this is called first order linear differential equation. So how do we solve something that's first order linear? There's a process that we go through to solve it. So let's look at an example. Let's say we have y prime plus 1 over x times y is equal to 24x plus 18. So we've got it in proper form. I like to call this proper form, where there's a 1 in front of that first derivative. Notice that that function in front of y is in terms of x, and that function that's on the other side of the equals is in terms of x. So that's how we know this is first order linear. So this is our standard form. We're going to start by finding something called the integrating factor, and I'm going to abbreviate that IF. The integrating factor, we're going to take E, and we're going to integrate, and we're going to put that P of X in front. So this guy is the exponent on the E. Now, when I integrate 1 over X, I'm going to get the ln of the absolute value of X. And E to the ln of X is just X. And we're just going to simplify that and use a positive X, which is going to cause some domain restrictions, but we're restricting the domain anyway. And we talked about this before, how a lot of times in real life, when we think about the independent variable, which in this case is X, we think about it in terms of positive. Usually in engineering, the independent variable can represent something called like time. And we know we can't go backwards in time. So that's why this is an okay move here. Our next step is to multiply through. So we're going to multiply everything by that integrating factor. So I'm going to multiply that differential equation by the integrating factor. So I'm going to multiply, I'll write it like this, and then we'll simplify it. I'm going to multiply through. I'm going to have xy prime plus x times 1 over x, which is 1 times y, is equal to 24x squared plus 18x. Now, the reason we do that is because we're going to do a clever rewrite on the left-hand side. This guy is really going to be the integrating factor times y. And we're going to think about taking the derivative of that product. Now, why would I do that? Well, this derivative ends up being what we had in that step before on the left-hand side. If I use the product rule, it's first times derivative of the second. So let me write that over here. Let's check that. Xy prime would be first times derivative of the second. Derivative of y is y prime. Plus the second times the derivative of the first, and the derivative of x is 1. And you can see how xy prime plus y is exactly what we have in the step above. So this is really a product rule that's been applied. So we're undoing that. And then we're going to integrate both sides. And we're integrating with respect to x, so I'm going to multiply both sides by dx. If I integrate something I want to take the derivative of, I'm going to be left with just that xy. When I integrate the other side, using the power rule, adding 1 to the exponent divided by the new exponent, don't forget your plus c. And then I'm going to simplify this. 24 divided by 3 is 8. And 18 divided by 2 is 9. So I have xy equals 8x cubed plus 9x squared plus c. And I'm going to divide everything by x to get y by itself. So I'm going to have 8x squared plus 9x plus c. So there's my c over x. We're dividing each of those terms by x. So there is my antiderivative. Let's do one more example of that. Let's say we have this differential equation, y prime plus tangent of x times y equals secant of x plus 5 cosine of x. So we're in proper form. So I've got a 1 in front of that y prime. The y terms are on the same side. So that tangent of x is my p of x. So when I find my integrating factor, it's going to be e to the integral of p of x. In this case, I'm integrating tangent. And when I integrate tangent, I'm going to get the negative ln of cosine. And then I'm going to simplify this. This negative is really an exponent on that argument of the ln. So this would be the ln of cosine of x to the negative 1. And we know e and the ln, e to the ln of something is going to be just that something. So this is going to be cosine of x to the negative 1, which is the same thing as secant of x. So there's my integrating factor. Step 2, we're going to multiply through by the integrating factor. So I'm going to multiply that differential equation through. So we're going to have secant of x multiplied by the differential equation y prime plus tangent of x times y is equal to secant of x plus 5 cosine of x. So we're going to have secant of x times y prime plus secant times tangent times y is equal to secant squared of x plus 5. And then secant times cosine is just going to reduce them 1. So that's going to be 1 times 5, which is 5. So now we're going to do our rewrite step. So this rewrite step, we're going to take the derivative of the integrating factor times y. And this is always a good place to check because this step, that has to be equivalent to what we have above. So let's try it. If I take the derivative of secant of x times y, the product rule says it would be first times derivative of the second, so secant times y prime plus second, which is y, times derivative of the secant, and derivative of the secant is the secant tangent, so you can see how this is equivalent to the step above. And now we're going to integrate both sides, and we are going to do that with respect to x. When I integrate something I want to take the derivative of, I'm going to get just what's inside that bracket, secant of x times y. When I integrate secant squared, I'm going to get tangent, and integrating 5 is going to give me a 5x, and then don't forget the plus c. And then now we're going to divide everything by secant. I'm writing every term so we don't forget. So we're going to get y by itself. I need to simplify tangent divided by secant. Tangent is sine over cosine. Secant is 1 over cosine. And you can see how this reduces to just sine of x. I have 5x over secant, which is 5x times cosine of x. And then c over secant, which is c times cosine of x. So there's my final answer for that. So let's talk about those steps. So the first thing you have to do is make sure it's in proper form. Make sure the differential equation, I'll abbreviate that DE, is in proper form. We call it standard form, where it's y prime plus p of x y is equal to q of x. It's having a 1 in front of that derivative. The y stuff is on the left-hand side, and all of the x stuff, the remaining things that don't have a y or a y prime attached to it, is on the right. And then your next step is to find the integrating factor. Integrating factor is always e to the integral p of x dx. You're going to find that, you're going to simplify it, and then step 3 is to multiply through. So multiply that differential equation by the integrating factor, and that's going to allow you to rewrite that left-hand side. It will always be the integrating factor times y. That's a good place to check, because if this does not, when you take the derivative, give you the step above, then there's something wrong in here. You'd have to go back and find where the mistake was. And then you just integrate both sides. So Bernoulli equations are really similar to that. Notice that that standard form, or that proper form that I like to call it, is the same. The difference is that we have y to some kind of power over here. We're going to do a clever substitution. We are going to let u equal y to the 1 minus n. And then when we make that substitution, it is going to turn this into a first order linear. So then we will be able to solve that in terms of u, and then we'll be able to back substitute back. So let's look at an example. Let's say we have the equation y prime plus 9x to the 8th times y is equal to x to the 8th times y to the 7th. So notice this is Bernoulli. We've got that y to the 7th here. We're going to do a substitution. We are going to let u equal y to the 1 minus n. So n is going to be the exponent that's on that y on the other side. So this is going to be y to the 1 minus 7, which is y to the negative 6. So here's what we have. We're going to say u is equal to y to the negative 6. And then everything else is going to come from that statement. So let's do a few more things to this. If that's true, then to get y by itself, I would raise both sides to the negative 1 over 6 power. So I've got y is equal to u to the negative 1 over 6. And then let's take the derivative of that. The derivative of y prime would be the derivative of u to the negative 1 over 6. We would bring that exponent down. We would subtract 1 from the exponent. And then we're going to show we took that derivative with respect to that independent variable by attaching a u prime. Remember, that's an implicit differentiation. So we've got our substitutions here. We started by letting u equal y to the negative 6. So then y equals u to the negative 1 over 6, and we've got y prime equals negative 1 over 6 u to the negative 7 over 6 times du. So let's substitute in what we know. Everything's going into that differential equation. Y prime is negative 1 over 6 u to the negative 7 over 6 times u prime. Then we have plus 9x to the 8th times y, but remember y is equal to u to the negative 1 over 6, and that's equal to x to the 8th times y to the 7th, but y is u to the negative 1 over 6. So I'm going to clean this up a little bit. We have negative 1 over 6 u to the negative 7 over 6 u prime plus 9x to the 8th u to the negative 1 over 6 equals x to the 8th u to the negative 7 over 6. So this is almost first order linear, but remember, you got to have a 1 in front of that prime value. So let's divide everything by that negative 1 over 6 u to the negative 7 over 6. I'm going to divide every term by that. So you can see how that's going to cancel in that first term, leaving me with a u prime there. I'm going to clean up this. I have 9x divided by negative 1/6. I'm going to do keep, change, flip. So it's going to be 9 times negative 6, which is a negative 54. And that's going to be x to the 8th. And then let's talk about the u's. When we subtract, when we have the same base and we're dividing, we're going to subtract the exponent. So we're going to have negative 1 over 6 minus negative 7 over 6, which is u to the 6 over 6, which is just u. Here, when I simplify, I'm going to have a negative 6 x to the 8th, and you can see how those u's are going to cancel. Now we're in the proper form for first order linear. So now we're going to apply our technique. So remember, with our technique, we found the integrating factor. E to the integral, and it's p of x. My p of x is negative 54 x to the 8th dx. I'm going to add 1 to the exponent and simplify. Negative 54 over 9 is a negative 6. So this is e to the negative 6 x to the 9th. Okay, notice in this one, that e is not going to cancel. I do not have an ln up here, and that is perfectly fine. It's still going to work out. We're going to trust the process. Now we're going to multiply through. So we're going to have e to the negative 6x to the 9th multiplied by that differential equation, which is here, u prime minus 54x to the 8th u equals negative 6x to the 8th. I'm going to multiply everything. E to the negative 6x to the 9th u prime minus 54x to the 8th e to the negative 6x to the 9th times u equals negative 6x to the 8th e to the negative 6x to the 9th. I've had a lot of students over the years ask me, is it really necessary for me to multiply that out when I know I'm rewriting the left-hand side? And my answer is always yes, for two reasons. If you don't multiply this out and see this in the step, a lot of people forget to multiply that right-hand side by the integrating factor. And the second reason is you need to be able to see that when you do your rewrite, which is the integrating factor times your y, which in this case we've got a u here, that this should be equivalent to this. So it's a great place to stop and say, am I on the right track? I don't recommend shortcuts, especially on problems like this. So let's check it. First times derivative of the second, so that exponential times u, the derivative of u, plus the second, so u times the derivative of e to the negative 6x to the 9th. The derivative of e to the u is e to the u, and the derivative of that exponent is that negative 54x to the 8th. So you can see how this is equivalent to the step above. Now we're in a place where we can integrate. When I integrate that left-hand side, I'm going to have e to the negative 6x to the ninth times u. If I think about integrating this here, I'm going to pull that negative 6 out, and I'm going to rewrite this. This is e to the negative 6x to the ninth times x to the eighth dx. So I would need the derivative of u. So my exponent on that exponential is the u. I would need a negative 54. I would compensate with a negative 1 over 54. So I'm going to have e to the negative 6x to the ninth times u is equal to 1 over 9. When I integrate, I get e to the u plus c. Now we're going to divide everything by e to the negative 6x to the ninth. We're going to have u equals 1 over 9 plus c e to the 6x to the ninth. Notice I brought this to the numerator by making that exponent positive. We want this in terms of x. So remember, we had a substitution for u. If we go back all the way up here, we said u was equal to y to the negative 6. So we're just going to substitute that in. So y to the negative 6 is equal to 1 over 9 plus c e to the 6x to the 9. So there's my final answer.